Alright. So today we're going to probably have three videos. This scheduling model in LLVM. Now I haven't chosen the other two from Hacker News, but I'm still kind of examining few of them. So we'll see how that goes. A message. Okay, fair enough. Alrighty, so let's go through this. Scheduling model in LLVM part 1. Not sure who wrote this, but let's have a look. It's by Min Jesus. He works as a compiler engineer at Sci5, and he's currently based in the beautiful Southern California. Good for him. I'm jealous of that. I've been actively contributing to LLVM for over 5 years. I served on the program committee for multiple LLVM developers meetings. I wrote the LLVM book in 2021 titled LLVM Techniques, Tips, and Best Practices, C-Lang and Middle End Libraries. I'm also the code owner and primary maintainer of LLVM's M68K compiler backend. I received my PhD in computer science from University of California, Irvine. And his advisor was Dr. Michael Franz. Pretty good. Okay. So, Min Jesus. Scheduling model in LLVM part 1. This is interesting. This was published yesterday, so you have to probably make this two videos. Let's go through the article. Instruction scheduling is essential to modern compilers. It tries to hide latencies and increase the throughput of a straight line code by reordering the enclosing instructions. In order to do that, compilers have to know a whole bunch of information ranging from individual instructions latency to microarchitecture details. The system that describes this is called a scheduling model. In LLVM, a scheduling model is used by not just the instruction scheduler but also target-specific optimizations like machine combiner and components like MCA, machine code analyzer. So what this is. It should have been used in more places like instruction selection and cost models in the middle end, but that's a story for another day. Okay. Which makes it an important factor in performance tuning for low level code. This series about LLVM's scheduling model, hidden tracks, affects other parts of LLVM, and how can we fine-tune this model for better performance. I'll cover how scheduling models are used in other parts of LLVM in later posts. Alright, so one thing I wanted to do is that I have a blog and I probably need to keep a directory of these videos, so it's very important to keep the source of these because I can later maybe come back to these, and because most of these articles that I read, the authors are very, very strong in their field. I don't know, but they know their field very well, and it's kind of, what is it called? It's kind of low effort for me to just read one article and not to follow up on it. So from that, I'm planning to have these articles, sources and websites and blogs in my own blog, so I can follow up on these and one day not even rely on Hacker News anymore. So that's that. To find these articles, because somebody finds these and put them on Hacker News, I'll try to be one. I'll try to be one step ahead of that. All right. Uh, where were we? I'm focusing on the scheduling model itself first and talk about how. Let me just bring this microphone closer. And talk about how to specify scheduling information for individual instructions. Let's start with a really basic example. The basics. Scheduling models are part of the target definition. They are associated with one or more target processors. Multiple processors can also share the same scheduling model. Take RISC-V as an example. We can find one of its scheduling models, Sci-Fi 7 model. Alright, I got an H to find out what Sci-Fi does. Maybe not in this one. Sci-Fi. Leading the RISC-V revolution. Interesting. Sci-Fi delivers superior high-performance compute density for modern workloads. Let's see. Okay, so this seems to be an IP company. I don't. Maybe they do have products. Like maybe they do make their own chips, but I feel like they are more on the design part. I believe so, right? I feel kind of stupid for not knowing what Sci-Fi does because I think I've seen their chips. I'm pretty sure I've seen their chips. Yes, Sci-Fi. Okay. Valued at 2.5 billion. Okay. That's good enough for now. Alright, so Sci-Fi 7 model covers a wide array of processors from Sci-Fi E76, a 32-bit microcontroller, to Sci-Fi X280, which is a high-performance processor designed for AI ML workloads. To describe per instruction scheduling information like latency, naively we can express such information with descriptions like opcode add has latency of X. It's all fun and games until you realize there are tens of thousands of opcodes in some of the targets. Interestingly, RISC-V has one of the biggest sets of opcodes. A large portion of them are pseudo instructions for RVV. What is RVV? RVV. Not quite. LLVM. Vector extension. RISC-V vector extension. RISC-V vectors. Okay, I see. Let's take a look here. Mapping to LLVM intermediate representation types. RVV adds 32 VLAN. Not sure what that is. Where VLAN is an unknown constant to the compiler. To be able to represent VLAN-sized values, the RISC-V backend takes the same approach as ARC64's SVE uses scalable vector types. Scalable vector types are of the form VScale XNXTY, which indicates a vector with a multiple of n elements of type TY on RISC-V, and TY control LMUL and SUW respectively. LLVM only supports ELAN 32 or ELAN 64, so VScale is defined as VLAN by 64. Note that means VLAN must be at least 64, so VLAN 32 isn't currently supported. So I believe these are just the integers. That will float half. LMUL. What is an LMUL? LMUL is a multiplier that allows you to pack multiple vector registers in the group. The values for LMUL can be 1/8, 1/4, 1/2, 1/2, 4, or 8, offering flexibility in configuring vector operations. Not quite sure, but okay, so we have the vector extensions. We have the what's this stand for? Maybe if we understand what is the length multiplier. I see. Okay. So let's move on. We were here. So it doesn't scale well. More importantly, many instructions share the same scheduling characteristics. For example, simple arithmetic operations like add, sub, and shifts usually have the same latency in most modern architectures. Instead of spelling out pair opcode information, LLVM chooses a different path that characterizes as instructions scheduling properties with operand reads and writes. First, each operand in an instruction is assigned with a token. Oh, I see. Instead of spelling out pair opcode information, LLVM chooses a different path that characterizes an instructions scheduling properties with operands reads and writes. So LLVM assigns the instruction scheduling with some operand reads and writes, and each operand is assigned a token kind of labeled, so you can probably schedule it better. You can make it in tune with other instructions. Take the div instruction. Div. Alright. So arithmetic logic unit RR do crazy things. These are binary. 3 values div. Okay. Let's just have that in the back of our mind. In RISC-V shown below as an example, write IDIV is the token assigned to the first operand, which is also the destination register. Hence a write operand, also called definition. The two read IDIV follow are tokens for the two source registers, both for read operands or use. Oh, this is what it was, okay. This was in this dev thing, wasn't it? I believe so. A write token is a sked write table gen instance, while a read token is a sked read instance. With these sked write and sked read tokens, a scheduler model then assigns processor specific information to them, like latency and the hardware resources they use. Take Sci-Fi 7 model we saw earlier as an example in the file where the model is defined. LLVM library target RISC-V scheduling Sci-Fi.td. What is the .td file extension? TD files contain table gen code. All right. Integer division. Define write res, write idiv, Sci-Fi 7 pipe b, Sci-Fi 7 idiv, let latency equals to 66, let release at cycles equal array 165. This is for integer division, and we have a write, and we have a write ID. You have the Sci-Fi stuff, we have the latency, we have the release at cycles. The write res table gen class takes a sketch write, in this case write ID IV, and assigns it 3 different kinds of information. Latency of 66 cycles, the hardware resources it uses, Sci-Fi 7 pipe B, and Sci-Fi 7 IDIV. The release at cycles field specifies the number of cycles this instruction spends on each hardware resource it uses. In this case, write IDIV spends 1 cycle on Sci5 7 pipe B and 65 cycles on Sci5 7 IDIV. What about read IDIV and schedule read instances we saw earlier? By default, LLVM's scheduling model assumes that operand reads finish instantly. So a schedule read cannot be assigned a latency property nor consuming any cycle the same way as a sched write, which means that effectively more operands dictate the instructions of scheduling properties, and it's expected to represent majority of the changes an instruction makes to the processor state. So it's safe to say that in this case an dev instruction has a latency of 66 cycles. Was division, right? I believe so. Alright, so far we have covered the most basic part of a scheduling model, specifically on how to specify the scheduling information for an instruction. We can summarize it into 3 quick steps. Assign a schedule read and a schedule write to your instruction. In your scheduling model, whenever I yawn, that means I'm learning a lot. That's not a sign of weakness or exhaustion. Let me tell you that. In your scheduling model, find the processor resources, sched write, use, and map. And if you're not yawning enough, you're not learning enough. Let me tell you that. And map those resources to sched write using write res along with other info like latency. I have intentionally left many details aside, like what exactly is a hardware resource. Example, Sci5 7 pipe B. These details are strongly related to what we are going to cover in the next section, the microarchitecture of a processor. Oh, interesting. Give me some of that. Model and microarchitecture. Recall the goals of instruction scheduling are to minimize latency, maximize throughput, and eliminate as many potential hazards in the processor's pipeline as possible. These goals have a lot to do with how many instructions move within the processor's pipeline. For instance, extra cycles might be spent on fulfilling raw read after write data dependencies, or certain units like an integer division unit might be overwhelmed and stall the entire pipeline. And this is where the processor's microarchitecture comes into play. Specifically, we are focusing on superscalar architecture here, which has a typical structure shown below. Fetch, decode, dispatch, issue. So maybe he could have put this on the arrows. Or maybe I'm just not getting this. Int, floater point, ls unit, execute, ROB. What is ROB in microarchitecture? Or microprocessors, huh? The reorder buffer tracks the state of all in-flight instructions in the pipeline. The role of the ROB is to provide the illusion to the programmer that his program executes in order. After instructions. Okay. Because you know how probably. Yes, exactly. So your program is not actually run sequentially because there's possible ways that the compiler can pipeline things differently. So it can use of, I don't know if the correct word is parallelism, but they can have parallel pipelines, so your instructions and everything is gonna look like it's sequential, but actually it's not. So the role of the ROB is to provide the illusion to the programmer that his program executes in order. After instructions are decoded and renamed, they are then dispatched to the ROB reorder buffer and the issue queue and marked as busy. Alright, the above structure has an issue width of 3, meaning it can fit at most 3 instructions to later stages at a time. Microcodes or UOPs are generated at the decode stage. At this moment, we are a little hand waving on the definition of dispatch and issue. As we'll see several of their variants later, there are three different functional units in the execution stage of integer, floating point, and memory instructions. Load and store unit. All of them are fully pipelined. Despite the fact that scheduling model has a strong connections with microarchitectures, we don't want our model to cover too many microarchitecture details. It was microarchitecture. I don't know why they wrote microprocessor. It's the same. It's simply too expensive. What we want is a model that can raise red flags when we come up with a bad scheduling. It abstract away all the nitty gritty details and present just the information we care. Alright, let's read that again. Despite the fact that the scheduling model has a strong connections with microarchitectures, we don't want our model to cover too many microarchitecture details. It's simply too expensive. What we want is a model that can raise red flags when we come up with a bad scheduling, yet abstract away all the nitty gritty details and present just the information we care. What kind of red flags, you may ask? The most important thing is probably whether we have enough resources to even run an instruction. Remember, the whole idea of superscalar is to run instructions of different types in different function units in parallel. Integer UOPs go into integer units and floating point UOPs go into another floating point unit. Where these units can run independently, each of these units has one or more pipes. So I was right. It's in parallel. The whole idea of superscalar is to run instructions of different types in different function units in parallel. Integer UOPs go into integer units and floating point UOPs go into another floating point unit. Where these units can run independently, each of these units has one or more pipes that actually run the UOPs in many places. Functional units and pipes are interchangeable. If there is not enough resource, we won't be able to dispatch an UOP into any of the pipes. After all, processors have only a limited number of pipes for a specific type of instructions. Let's look at a concrete example. Sci-Fi's P6670 RISC-V processor. I really want to read out the whole image. So next line predicate. Okay, so it has a branch prediction, branch direction predictor, indirect jump target predictor, return addresses stack, and now we have a cache of size 32 kilobyte, and that does the instruction cache. 32 bit per cycle. Goes from your private L2 cache up to 512 kilobyte, and you have your data cache that's 32 kilobyte, and you have your L3 that is up to 16 megabyte. Oh, wow. I don't know. Take this with a grain of salt, but probably 16 megabyte is something compared to 20 years ago, man. Like, at least it should be a great technological advancement compared to that time, you know. So you have the integer dispatch buffer, ISS, BR, arithmetic logic unit, multiplication division, I2F. What is it? I2F is I2F. Oh, maybe integer to float something. Micro architecture. Integer to float. I'm a genius. Anyways, 208 integer register renames, 208 FP register renames, 2 times 64 vector register renames. We have the floating point dispatch buffer, the vector dispatch buffer, arithmetic logic unit division, vector to scalar maybe, fmac, fadd, fmol. What is fmac? Fmac. In micro architecture. Bulldozer architecture. What's this? What is fmac? Oh, come on, you gotta give me something. Fmac in CS. Here we go. Here we go. In computing, we can turn this off. Oh wow. In computing, especially digital signal processing, the multiply, accumulate, and multiply, add, MAC and MED. Doesn't rhyme, but still. Operation is a common step that computes the product of two numbers and adds the product to an accumulator. The hardware unit that performs the operation is known as multiplier accumulator. The operation itself is also often called a MAC or a MAD operation. The MAC operation modifies an accumulator A. So when done with floating point numbers, it might be assigns to A value of A, all value of A plus B times X. It might be performed with two roundings, typical in many DSPSs, digital signal processor. Or with a single rounding. When performed with a single rounding, it is called fused multiply add or fused multiply accumulate. FMAC or FMA. Fused. Because with a single rounding, you're fusing it. You're not using two roundings. Modern computers may contain a dedicated MAC. Multiply accumulator consists of a multiplier implemented in combinational logic followed by an adder and an accumulator register that stores the results. The output of the register is fed back to one input of the adder so that on each clock cycle, the output of the multiplier is added to the register. Combinational multipliers require a large amount of logic but can compute a product much more quickly than the method of shifting and adding typical of earlier computers. But can compute a product much more quickly than the method of shifting and adding typical of earlier computers. Interesting. Combination requires more logic, but it can do it more quickly than shifting and adding. That's crazy. Percy Ludgate was the first to conceive a MAC in his analytical machine of 1909 and the first to exploit a MAC for division using multiplication seeded by reciprocal via the convergent series. The first modern processors to be equipped with MAC units were digital signal process DSP. But the technique is also common in general purpose processors. This guy is quacked. Of course he's Irish. Anyways, alright, so we got the FMAC. We got the FMOL. It's fused, it's not floater. So P670 is an out-of-order processor targeting consumer devices like smartphones. It has 4 integer pipes, 2 floating point pipes, and 2 vector units. And this is how integer pipes look like in its scheduling model. Define Sci5 P600 IEXQ0 to be proc resource 1. Define IEXQ1 to be process resource 1, and then keep going till you get to Sci5 P600 integer arithmetic Process resource group. Uh, so you put all of this together, I believe, to get here. Alright, so in LLVM, a process resource instance in TableGen represents a unit that can execute UOPs, hence an equivalent to a single pipe in most cases. Here, each integer pipe in P600 is represented by Sci5 P600 IEX Nevertheless, it's not the only instance you can dispatch UOPs to, because sometimes you can dispatch UOPs into a collection of pipes in which any of the pipes in that group can execute the dispatch UOP. Such groups are represented by ProsRes group instances in TableGen, like the Sci5 P600 integer arithmetic we see above. When an instruction like add who uses write IA write integer arithmetic logic unit consumes a Sci5 P600 integer arithmetic shown in the snippet below, it means that such instruction can be dispatched to any of the Sci5 P600 IEXQ 0 to 3. Sure. Okay, so I need to probably just stare at this a little bit harder, like, so I can like take a mental image of all this. Yes, when there is no available pipe, a stall or a hazard occurs. In this case, it is considered a dispatch hazard since you can dispatch more instructions. You avoid such hazards. Each pipe usually has a buffer or queue to store a certain number of candidates. Knowing the size of that buffer is crucial to our scheduling model, because then we can make a wiser decision on distributing the instructions evenly across all pipes, rather than jamming them into a single one just like freeways in LA. To avoid such hazards, each pipe usually has a buffer or a queue to store a certain number of candidates. Knowing the size of that buffer is crucial to our scheduling model, because then we can make a wiser decision on distributing the instructions evenly across all the pipes. Most superscalar and out-of-orderness are two independent concepts. Superscalar is about increasing the width of your execution units. Out-of-order is about the order of execution. You can have in order superscalar processor, which are pretty common, as well as out-of-order non-superscalar processors, which barely exist but no one can stop you from making it. In order superscalar and out of order non-superscalar, right? I don't know. Okay. All right. Where were we? We were at 4. Processors with buffers, queues like this have a more well-known functionality, reordering instructions in an out-of-order processor. Each of these buffers is used as some sort of staging area of the scheduler to preemptively issue instructions with no dependencies on the orders. In the hope of hiding latencies, aside from the size of the buffer, how to organize these buffers? Several pipes might share a buffer is just as important as their sizes. In the next section, we are going through processor resource buffers of different sizes and layouts. Processor resource buffers. Let's sort out some terminologies first. The buffer or scheduler queue we are talking about here is often known as a reservation station too. A reservation station stores instructions whose operands might not be ready yet until those operands are available. Reorder buffer, on the other hand, is a kind of unit with slightly confusing name. Reorder buffer reorders the results of an instruction. It's usually depicted at the end of the execution stage, as shown in the previous diagram. Nevertheless, we need to reserve a slot in the reorder buffer before we can even dispatch an instruction. Therefore, to some extent, the size of reorder buffer also controls how many instructions are allowed into the execution stage. Back to the buffers, in LLVM's scheduling model, we use the buffer size field in a processor resource or a PROS-res group instance to specify the size of the associated buffer. Special values are also used to denote unconventional buffer layouts or even the absence of buffers. LLVM currently supports 4 different kinds of buffer layouts: decoder reservation stations, unified reservation station, in-order core, and latency device. Let's go through each of them now. Decoupled, it's so the couples together, we decouple now, and then we have a reservation system, probably. Unified, there are these rebels, you're the king, want to be nice to each other. We unify and we put them in the reservation stage. In-order core, so everyone has a core, you don't want to be out of order, man. And then we have the latency device, which is you don't want latency, man, because you want to be fast, man. So that's good, man. Decoupled reservation stations. So it's decoupled, then unified, then in-order core, then latency devices. Did you like that? Did you like that? Okay. Alright. Decouple reservation stations. So we go from this to dispatch, and then you buffer it, and then you have processors, resource 1 processor, resource 2 processor, resource 3. When we assign a positive buffer size to individual processor resources or processor resource groups, we are modeling processor resources with their own scheduler queues. Here's an example from PowerPC Power 9's scheduling model. Only one branch unit is defined. Processing resource, let buffer size be 16. And branch unit is, you have a process. I need to learn LLVM, man. Fuck. Yes. I might use a series on LLVM on YouTube and just record myself over that, so I can explain this as good as I can to you guys. I'm sorry, guys, I'm letting you down. Anyways, here the execution unit for branch instructions has its own scheduler and has 16 entries in its buffer. A more common arrangement is assigning buffer size on a processor resource group. For instance, in AMD Zen 2 CPU, there are total of 4 general integer execution units with their own schedulers. Each scheduler has 16 buffer entries. Alright. LSEX front end. So you have the next address logic. We have your caches probably. These go back and forward. These are one direction. You have your micro tags. You have your prediction queue. You have your instruction cache. It's 32 kilobyte 8-way, 64 B-line. Instruction byte queue. Pick 4-way decoder. What happened? And then you have the microcode, micro operating queue, stack engine memory file, microcode sequencer, and you go to the dispatch mode. You retire code, then you rename it. Then this is probably your ALU physical register file, 180 entries, forwarding muxes. What are muxes in micro what is mux? Multiplexer. In electronics, a multiplexer, or mux is spelled sometimes as multiplexor, also known as a data selector, is a device that selects between several analog or digital input signals and forwards the selected input to a single output line. The selection is directed by a separate set of digital inputs known as select lines. A multiplexer of 2 to the n inputs has n select lines, which are used to select which input lines to send to the output. A multiplexer makes it possible for several input signals to share one device or resource. For example, one analog to digital converter or one communications transmission medium. Instead of having one device per input signal, multiplexers can also be used to implement Boolean functions. Oh, I see. I have no idea. There are data selectors. Selection is directed by a separate set of digital inputs known as select lines. A multiplexer of 2 to the n inputs has n select lines, which are used to select which input line to send to the output. Okay. It's the data selector. So where were the muxes? Muxes were forwarding muxes. They were data addressing. They are data selecting. If you're a mux, you're a multiplexer. So you're data selecting. You're a selector. Okay. Fused add, fuse multi add, fused add. I'm not sure if that ADD is add, but I'm sure let's call it add. Then you go from this AGUs. What is an AGU? AGU in micro architecture. Okay, address generation unit, sometimes also called address computation unit. ACU or AGU is an execution unit inside central processing units that calculates addresses used by the CPU to access main memory. Oh, I see. So maybe when you do the assembly things to go fetch something, it's actually doing this. Probably. Yes. Load queue, you have 44 entries. LD1, LD0 pick, LD1 pick. You have your refetch, you have your store queue, you have your steep pick, you have those store commits, you have some fun stuff. Sure. In Zen2's LLVM scheduling model, these schedules are represented by 4 processor resource instances. Zen2 ALU 023. Despite the fact that there are 4 separate schedulers in real hardware, Zen2 scheduling model doesn't assign buffer size equal to 416 to each Zen2 ALU instance, but instead group all 4 instances into a single process resource group called Zen2 ALU and design a buffer size of 16 times 4. So define Zen2 ALU Let buffer size be 64. Your processor resource group is Zen2 ALU0, Zen2 ALU1, Zen2 that. Okay, so is this for Zen2? This should be, huh? This is from Wiki Chip. Oh, this is annoying, but excuse me. Oh, enable. Wow, wow. Eyes. Okay. Um. Mm. Block diagram. This is crazy. Architecture. Chips. Ahem. This is crazy. What? Who's editing this? Well, okay, I guess Wikipedia, Wikichip is great. So the guy said he has 16 buffers for 4 integer units, and so where are the integer units in this? This is 4, but that's your ALU, isn't it? And then it said 16 buffer units. Yeah, by the way, this makes you smart. 16 buffer units. Where did that come from? Buffer units, DTLB, DC tags, MAB, L1 data cache, WCB, stored comment, stored queue, stored pick, stored p, prefetch, AGU calculates the address of the memory that you're supposed to access. Address generation unit. It's different than arithmetic logic unit. Address generation unit, or C was address computation unit. What is ALQ? Arithmetic logic queue. Rochester. Load store queue management as energy efficient design based on a state filter mechanism. Sure. Okay, you can probably move on. You spent fair share of trying on that. Okay, micro operation buffer size attribute. Did we do this or did we not do this? We didn't. We are at the unified reservation station. By default, buffer size is set to -1, representing a layout where all the processor resources effectively share the same buffer as illustrated in the diagram below. Dispatch issue unified reservation station processor resource 1, processor resource 2, processor resource 3. In this case, the actual size of such buffer is dictated by micro op buffer size, which is a global attribute to the entire scheduling model rather than individual processor resource. Def Sci5 P600 model, schedule machine model, let issue width equal to 4, let micro op buffer size be equal to 160, and then you do these other things. This micro op buffer size attribute is primarily used to throttle the number of UOPs to be dispatched. There are, however, many factors that control this throttle at the same time, notably reorder buffer and register renaming. We've explained the effect of reorder buffer earlier. For register renaming, if there aren't enough physical registers for us to rename, a dispatch hazard also occurs. Consequently, the value of micro op buffer size should be the minimum of reorder buffer size of register renaming pool, and the actual size of unified reservation station. In order cores. So far we have been discussing out of order cores, which is one of the primary reasons why we need buffers in the first place. But in order cores are still a thing because it dramatically simplifies the chip design and reduces the area, which are top on the list for products like embedded devices. You're also getting more popular in cases where you want to save areas for specialized units like big vector units or even matrix multiplication units. Sci5's X280, which we've seen it's a scheduling model previously, and X390 are good examples where they save area by adopting an order design and enjoying a whopping 512 and 1024 bit vector respectively. For in-order cores, you simply set buffer size and micro op buffer size mentioned earlier to 0. When an UOP, what is an UOP? I swear to God, I've taken hardware system course. I just keep forgetting everything. What is UOP in C computer? Yeah. User operation prohibition. User operation prohibition (UOP) is a feature that prohibits the user from performing certain functions during certain parts of. Come on. Here we go. Excuse me. Micro operation, micro op or UOP cache, a micro operation cache is a special cache that stores micro operations of decoded instructions received directly from the instruction decoders or from the instruction cache. Okay, what does a decoder do? Sure. A decoder is a multiple point input, multiple output logic circuit that converts coded input into coded outputs, where the input and output codes are different. The input code generally has fewer bits and than the output code, and there is one-to-one mapping from input code words into output code words. Yeah, interesting. Decoders are used to convert an analog signal to digital data, which can then be processed by a computer. Examples: the following examples of encoders and decoders: binary decoder that uses a combination of AND, OR, NAND, NOR, and NOT gates to convert analog signals. So a decoder changes the you know what? I came up with a brilliant idea. What if I make shorts on the little thingies here? Yeah. Very short videos, and then it's gonna just be, yeah. That's good. Okay, so decoder just changes your analog signal. Excuse me. Anyways, a decoder changes your. It basically decode your analog signal to binary signal. So it's kind of signal processor. Well, not any signal processor because we probably have analog to analog signal processor. This is probably what is it called? Well, it's more focused from analog to binary. That I can say, I guess. For in-order cores, you simply set buffer size and micro operation buffer size mentioned earlier to 0. When a UOP is handed to an in-order unit in LLVM's scheduling model, dispatch and issues are considered happening at the same time. The UOP then holds the processor resource until release at cycle before another UOP can be dispatched. In other words, oh god, why do I get so many messages? Excuse me, guys. The UOP then holds the processor resource until release at cycle before another UOP can be dispatched. In other words, the younger UOP would encounter a dispatch hazard until release at cycle has passed in or in the older UOP. Latency device, when buffer size equals to 1, we create a unique kind of resource known as latency device. Resources of this kind act like just an in-order pipeline, except two things. Since there is still a buffer, albeit being a real small one, a younger UOP waits in the buffer until the older UOP finishes, rather than encounters a dispatch hazard. LLVM's instruction scheduler always treats two adjacent UOPs that use this resource as producer and consumer, even if there is no data dependencies between them, meaning the younger UOP always waits latency cycles after the old UOP was issued as opposed to waiting until release at cycle has passed in a normal in-order pipeline before it can be issued. This kind of resource was designed to model in-order units within an out-of-order core. It's most commonly used for modeling on-pipeline units nowadays, which of course is in order. Yes, it's 2024 and there are still computations that are difficult to be pipelined, most notably integer. Sometimes even floating point divisions. It is possible to make integer divisions pipeline, but many of the times it's not worth the chip area. Okay. Some examples. Samsung Exynos M5 serialized on pipeline integer division unit represented by M5 unit D from here. Where is here? I feel like this is. Oh, it's not accurate. That's great. This video is gonna be about an hour, but this is crazy actually. These guys have all of this. AMD GPU, RISC-V, Spare-5, Spark, System Z, BPF, AVR, CS-Sky, DirectX, Hexagon. Wow. These guys have all these targets. That's cuckoo. So then you write your frame for LLVM and then it gets to the right target, I believe. RISC-V's rocket chip marks their integer and floating point division. Rocket unit unit 1 dev and rocket unit FPD IV squared as latency devices too. So wait, these guys wrote their thing in here. That's how he found it. It's probably going through this every day. This is 1,000 lines of code. This is arc 64. I don't know what's arc. Let me write this down. What is? Why do I not have any notepads? This is great. Epilogue. In this post, I went through the basics of LLVM scheduling model and show how to specify the scheduling information for individual instructions. On top of that, I explained different kinds of processor resource buffers and their use cases. In the next post, I will talk about how exactly these resource buffer kinds and latencies are used in LLVM's instruction scheduler and LLVM MCA, as well as their performance impact on the generated code, which helps us to make a better decision on designing new scheduling models. Alright, so there were a lot of new vocabulary here, but I'm not even quite sure what I've read. I need more compiler and LLVM brains and a little bit more chip design. But this is fun. Imagine just like putting these together and you're like, yeah, let's add a pipeline and then let's patent it, man. Like, it's cool. So we learned about the mocks. It's your data selector. Did you learn that? It is your data selector. So we went through RISC-V. Then we learned about Sci-5. We learned about latencies, I guess. We learned about read I div, write one div, or is it? I'm not sure. Then we learned that LLVM has a bunch of targets, a lot more than I expected. What else is in here? ARM, AVR, BPF, this guy. This is crazy. Target independent opportunities. Get the C frontend to explain HY pot. LLVM does square roots of x times x plus y times y when error no and precision don't matter. Miscellaneous matter will like this. This isn't safe in general, even on Darwin. C library implementation of HiPod, for example. Okay. Thank you. There's a lot of chefs, there's a lot of binary things here. What is FULL? Unsigned long? Probably. What else could it be? And we have this basic one, modeling microarchitecture. Recall the goals of instruction scheduling are to minimize latency, maximize throughput, and eliminate as many potential hazards into the processor's pipeline as possible. These goals have to do with how instructions move within the processor's pipeline. For instance, extra cycles might be spent on fulfilling raw read after daily data dependencies, or certain units like an integer division unit might be overwhelmed and stall the entire pipeline. Decode, rename, dispatch 4 bytes 160 into reorder buffer, integer dispatch buffer, load store dispatch buffer, floating point dispatch buffer, vector dispatch buffer. P670 is out of nowhere. Okay. Yeah, now I'm gonna record my analysis too. Let's sort out some terminologies first. The buffer or scheduler queue we're talking about here is often known as the reservation station 2. Reservation station stores instruction which operands might not be ready yet. Until those operands are available, reorder buffer ROB on the other hand is kind of a unit with slightly confusing name. Reorder buffer reorders the results of an instruction. It's usually depicted at the end of the execution stage, as shown in the previous diagram. Nevertheless, we need to reserve a lot of slot in the ROB before we can even dispatch an instruction. Therefore, to some extent, the size of reorder buffer also controls how many instructions are allowed in the execution stage. Back to the buffers. In LLVM's scheduling model, we use the buffer size field in a processor resource or a processor resource group. There was a fly. Then we learned about this fusion add. It's about like rounding it, and if you're multiplying, you can like add with one round of rounding. Then you learned about the address generating unit. And then ALQ is ALQ. What is ALQ in microarchitecture? Whew. It's not there, guys. What is it not there? Maybe I'm looking at the wrong thing. Adaptive loss over quantization. That's not it. Schedulers. AGQ. Wiki chips. Here we go. ACQ. No. AGQ. Address generation queue. Oh, here we go. Oh, so it's something related to Zen 2. Zen 2 is AMD's processor to Zen Plus and is a 7 nanometer process microarchitecture for mainstream mobile, desktops, workstation, and servers. Zen 2 was replaced by Zen 3. For performance desktop and mobile computing, Zen is branded as Athlon, Ryzen 3, Ryzen 5, Ryzen 7, Ryzen 9, and Ryzen Threadripper processors. For servers, Zen is branded as EPYC, and compiler support is it's on GCC and LLVM. Interesting. And we have brands. so from AMD. Yes. Client IO, server IO dive. This is great. Okay, and wait. Oh yeah, we were just going through these guys. So maybe this is something these guys came up with. I don't know. And then we had that fourth thing, the unified selection zone, and then not the epilogue. Unified. Here we go. Decoupled reservation stations. Unified reservation station in order core and latency device. Okay, so I guess that's understandable too. And then I will wait and get more knowledge to make the second video for part 2 of this article. So that's it for this video. Thank you.